Individuals inquire of me constantly, what's the distance to Mars? What's the distance to the Moon? What's the distance to Alpha Centauri? And NASA researchers will provide you these remarkably exact figures. They'll inform you Mars is 225 million kilometers distant or something similar. The Moon is precisely 384,400 kilometers. Yet here's the matter, and I'm not suggesting NASA is deceiving you. I'm not suggesting that whatsoever. However, there's this fundamental complication with how we gauge distances in space that NASA somewhat must navigate around. They cannot disclose the complete reality because the complete reality is considerably more intricate, considerably more uncertain, and considerably more fascinating than they typically have opportunity to clarify. Allow me to begin with something straightforward. If I wanted to gauge the separation between 2 points in this space, what would I do? I'd obtain a measuring tool, correct? I'd extend it and I'd tally the indicators. 1 meter, 2 meters, 3 meters. The measurement is direct. I can observe the entire distance with my own vision. Yet now envision the 2 points are so far apart that I cannot possibly extend a measuring tool between them. Not even an extremely lengthy one. That's when matters become complicated. That's when you must be ingenious. And that's where the genuine narrative commences. Here's the initial ingenious concept: triangulation. Let's assume a mountain exists far in the distance and I want to determine its distance. I position myself at point A and I observe the mountain. I gauge the angle from my position to that mountain summit. Then I traverse a known distance. Let's assume I walk 1 kilometer to point B and I gauge the angle again from that new location. Now I possess 2 angles and I understand the distance between my 2 observation points. With some geometry, some trigonometry, I can determine how distant that mountain must be. Straightforward, elegant, and it functions for modest distances. Astronomers employ this identical technique to gauge distances to neighboring stars. It's termed parallax. Envision you extend your finger before your face and you close one eye, then open it and close the other. Your finger seems to leap back and forth, doesn't it? That's parallax. It's the apparent change in position of an object when you observe it from different locations. Astronomers perform the same action, yet instead of utilizing their 2 eyes, they utilize 2 opposite sides of Earth's orbit around the Sun. 6 months apart, they observe a neighboring star and gauge how much it appears to shift against the backdrop of distant stars. The shift is minuscule, incredibly minuscule, yet it's measurable. And once you understand that shift, once you understand that angle, you can compute the distance. Yet here's where it becomes fascinating. This method solely functions for relatively neighboring stars. The more distant the star, the smaller that angle becomes. You're gauging angles so minute, they're nearly impossible to detect. And here's the matter regarding measurements. Whenever you're gauging something extremely minute, your uncertainty in that measurement doesn't diminish proportionally. The errors remain approximately the same magnitude. So if your angle measurement possesses an uncertainty of, let's say, 1/100th of a degree, that uncertainty doesn't shrink when you're observing a star twice as distant. The star is twice as distant, yet your angle is half as large, which signifies your percentage error has doubled. Do you perceive the complication? And this is where NASA begins to encounter difficulty disclosing the complete narrative. Because beyond a certain distance, and we're still discussing relatively neighboring stars, merely a few hundred light years distant, this parallax method ceases functioning. Well, the angles become so minute that the errors become enormous. So, astronomers devised a new tier on what they designate the cosmic distance ladder. Now, allow me to clarify this ladder because it's truly the essence of why NASA cannot provide you a straightforward response about distances in space. The cosmic distance ladder represents a brilliant concept, yet it's also fundamentally problematic. Allow me to clarify it by creating an analogy. Envision you want to gauge the elevation of a structure, yet you lack a measuring tape sufficiently lengthy. So what you do is obtain a small ladder and you gauge the initial 3 meters using that ladder. Excellent. You've established your baseline. Now you take a slightly taller ladder and you calibrate it against the initial one. You can now gauge 6 meters. Then you obtain a longer ladder calibrated against the second ladder and now you can gauge 12 meters. You continue stacking ladders atop ladders, each one calibrated against those beneath it, until eventually you can reach the structure's summit. The complication becomes apparent when you consider it. Each time you add a new ladder, you're introducing new uncertainty. Perhaps the second ladder isn't perfectly aligned with the initial one. Perhaps a minuscule error exists in how you gauge the initial 3 meters. That error doesn't disappear. it gets carried upward to the second ladder. And then that combined error, the error from the initial ladder, plus the new error from the second ladder gets carried upward to the third ladder. By the time you're stacking 10 ladders atop each other, the uncertainty at the summit isn't 10 times the original error. It's considerably worse than that. That's precisely what astronomers perform when they gauge distances in the universe. They construct a cosmic distance ladder. The initial tier is parallax, which functions for neighboring stars up to a few hundred light years. Once you surpass that, parallax no longer functions. The angles are too minute. So they needed to devise the subsequent tier of the ladder. The subsequent tier utilizes special stars designated Cepheid variables. These are stars that pulsate. They become brighter and then dimmer in a regular repeating cycle. Here's the ingenious aspect. The duration these stars require to complete one pulsation relates to their intrinsic brightness. If a Cepheid variable possesses a lengthy interval between pulsations, it's actually extremely bright. If it possesses a brief interval, it's dimmer. This relationship was discovered by an astronomer named Henrietta Leavitt in 1912, and it's proven incredibly useful. Yet here's the crucial point. To utilize Cepheids as distance markers, astronomers initially needed to calibrate them. They needed to examine Cepheids sufficiently close to gauge with parallax. They gauged those neighboring Cepheids with parallax, determined their intrinsic brightness, and then they verified that yes, indeed, the pulsation period correlates with the brightness. Now they could employ this relationship to gauge distances to other galaxies. If they observe a Cepheid variable in a distant galaxy, they gauge the pulsation period. They understand what the intrinsic brightness must be. And by comparing how bright it appears with how bright it intrinsically is, they can compute the distance. Sounds effective, correct? Yet do you perceive what just occurred? The distance to those Cepheids in the distant galaxy depends entirely on the accuracy of the parallax measurements of the neighboring Cepheids. If an uncertainty exists in those parallax measurements, if we've committed an error in calibration, that error now applies to every single Cepheid-based distance measurement we make. We've carried the error upward to the subsequent tier of the ladder, and it doesn't cease there. Once astronomers understand the distances to neighboring galaxies utilizing Cepheids, they can employ those galaxies to calibrate the subsequent tier of the ladder. This subsequent tier utilizes something designated Type 1a supernovae. These are incredibly bright explosions occurring in binary star systems when material from one star falls onto the surface of a white dwarf, a deceased stellar core. The explosion occurs at roughly the same brightness each time, which renders these supernovae useful as standard candles. If you understand how bright a supernova intrinsically is, and you gauge how bright it appears, you can compute the distance. Yet to utilize supernovae as standard candles, you initially need to calibrate them. And how do you accomplish that? You employ galaxies where you've already gauged the distance utilizing Cepheids. You gauge supernovae in those galaxies. You understand the distance. You gauge the brightness. Now you can declare, okay, supernovae are intrinsically this bright. Now you can employ that calibration to gauge distances to supernovae in considerably more distant galaxies. Do you perceive the complication now? Each tier of the ladder depends on those beneath it. An error at the base in the parallax measurements gets amplified as you ascend. By the time you're gauging distances to galaxies billions of light years distant, you're not merely dealing with the original parallax error. You're dealing with accumulated errors from parallax plus the error in calibrating Cepheids, plus the error in calibrating supernovae, plus errors introduced by cosmic dust, plus errors introduced by our incomplete understanding of how these stars actually behave. It's errors all the way upward. And here's something that genuinely troubles astronomers, something they don't frequently discuss publicly because it sounds uncomfortable. When different astronomers employ different methods to gauge identical cosmic distances, they don't consistently obtain identical answers, not even approximately. Occasionally, for example, there's something designated the Hubble constant. It's the rate at which the universe expands. Different measurements of the Hubble constant disagree by about 10%. That might not sound substantial, yet in astronomy, that's enormous. That indicates somewhere on our cosmic distance ladder a systematic error exists. We haven't discovered yet. Yet where is it? In parallax? In Cepheids? In supernovae? Nobody knows. And that's why NASA cannot simply inform you the universe expands at precisely this speed. They must qualify. They must provide you ranges. They must state plus or minus. Allow me to inform you about another source of uncertainty that renders this even worse. When astronomers gauge the brightness of distant stars and galaxies, they're not gauging light in a vacuum. The light must travel through space. And space isn't empty. Dust exists, gas exists, all kinds of material floating around in interstellar space exists. This material absorbs light. It's designated extinction. A distant galaxy might appear considerably dimmer than it intrinsically is because of all this dust between us and it. Now, astronomers possess methods attempting to correct for extinction. They can examine the light's color. Dust tends to absorb blue light more than red light, which is why distant galaxies appear redder than they should. Yet, here's the matter. Different types of dust absorb light differently. The dust near one star might differ from the dust near another star. So, the correction you apply depends on assumptions you're making about the dust's nature, and those assumptions might be incorrect. Add another layer of uncertainty. And then there's gravitational lensing. Light from distant galaxies travels through space, in straight lines typically. Yet when that light passes near something extremely massive like a galaxy cluster, that massive object's gravity bends the light similar to a lens-bending light. The light follows a curved path instead of a straight path. Occasionally this causes a distant galaxy to appear magnified. Occasionally it causes it to appear dimmed. And occasionally light from the identical galaxy follows multiple paths around the massive object. So you observe multiple images of the identical galaxy. Now when you gauge that galaxy's brightness, you have no idea if you're gauging it magnified or dimmed or what. That introduces uncertainty. Now I want you to understand something important. I'm not suggesting NASA researchers are incompetent at their work. I'm not suggesting they're incapable. Actually, they're remarkably capable. They've constructed these incredible space telescopes. They've dispatched spacecraft throughout the solar system. They've performed measurements of incredible precision. The Gaia Space Telescope, for instance, can gauge a star's parallax so precisely that if you position Gaia atop Buckingham Palace, it could gauge the width of a human hair atop the Empire State Building 5,000 kilometers distant. That's an incredible precision level. Yet here's the matter. Even with that precision level in our measurements, the fundamental complication persists. We still cannot circumvent the cosmic distance ladder. We still cannot circumvent carrying errors upward from one tier to the subsequent. The universe is simply too immense, and physics limitations are simply too confining, and no way around it exists. And one more aspect exists that renders this complication worse, something that truly reaches the essence of why NASA cannot inform you the straightforward reality. As you travel farther and farther from Earth, as you attempt to gauge distances to increasingly distant galaxies, you eventually reach distances so great that even the supernova method no longer functions effectively. The supernova becomes so faint that even our finest telescopes can barely observe them. So, astronomers devised yet another tier of the ladder. For the most distant objects, astronomers employ redshift. When a galaxy moves away from us, and all distant galaxies do, because the universe expands, that galaxy's light gets stretched, the wavelengths lengthen, the light appears redder. This is designated cosmological redshift. The redshift amount directly relates to how rapidly the galaxy moves away from us, and according to Hubble's law, the velocity at which a galaxy recedes is proportional to its distance. So all you must do is gauge the redshift, and you can compute the distance. Correct? Incorrect. Because to employ Hubble's law, you need to understand the Hubble constant. What is the Hubble constant? It's the proportionality constant connecting distance to recession velocity. And how do you gauge it? You gauge distances to neighboring galaxies utilizing the cosmic distance ladder tiers you've already constructed. You gauge their redshifts, and then you fit a line through the data to determine the constant. Yet if your distances to neighboring galaxies are uncertain, and they are because of all those errors accumulated up the ladder, then your Hubble constant measurement is also uncertain. And if the Hubble constant is uncertain, then all your distance measurements for the most distant objects in the universe are also uncertain, because you're computing them based on that constant. This is why different teams of astronomers employing slightly different methods or slightly different data obtain different values for the Hubble constant. And this is why if you examine NASA's official statements about distances in the universe, you'll observe them qualified with careful language. The distance to this galaxy is approximately this, with an uncertainty of approximately this much. They're not attempting to be evasive, they're being honest about the limitations of what we can understand. A concept in science exists designated systematic error, and I want to clarify it because it's crucial to comprehending this complication. Two types of errors exist in measurement. Random errors are matters occurring by chance. You gauge something and occasionally your measurement is slightly too high. Occasionally it's slightly too low. If you perform numerous measurements, these random errors average out. You can reduce random errors by taking more measurements. Yet systematic errors differ. A systematic error is an error that consistently goes in the identical direction. It's embedded in your method. For example, if your measuring tool is slightly too short, then every measurement you make with it will be too long. All your measurements will be offset by the identical amount. You cannot rectify that by taking more measurements because every measurement will possess the identical error in the identical direction. Now, here's the alarming aspect about the cosmic distance ladder. We cannot even perceive some of our systematic errors. We gauge distances utilizing parallax. We employ those distances to calibrate Cepheids. We employ Cepheids to calibrate supernovae. We employ Cepheids to calibrate redshift. At each step, if a systematic error exists in the method, that error gets carried forward and magnified. And we might not recognize an error exists until someone attempts a completely independent method and obtains a different answer. This has actually occurred. A famous case existed in astronomy history where two different groups of astronomers were gauging the Hubble constant, attempting to determine the universe's expansion rate. One group, employing one method, obtained one value. Another group, employing different methods, obtained a different value. It was a significant crisis in astronomy. These two measurements disagree by almost 50%. How could they possibly both be accurate? Well, one of them wasn't. And it required many years of careful work to determine which one possessed the error and where that error originated. I'll inform you what I find fascinating about all this. The complication isn't that NASA researchers are unintelligent or incompetent. The complication is more fundamental. It's about the universe's nature and measurement's nature itself. The universe is immense, genuinely immense, too immense to traverse with a measuring tape. We must employ indirect methods, and every indirect method possesses limitations. Every method functions only over a specific distance range. And when you combine methods to extend beyond that range, you accumulate errors. It's similar to a telephone game. You whisper a message to the initial person, and they relay it to the second person, who relays it to the third person, and so on. By the time the message reaches the final person, it's completely different from the original. That's essentially what occurs with the cosmic distance ladder. The original parallax measurements performed with such incredible precision by telescopes like Gaia resemble that initial whisper. Yet by the time the information has been relayed through 5 or 6 different ladder tiers, combined with calibrations and corrections for dust and gravitational lensing and assumptions about stellar evolution, the message has transformed. You've lost fidelity. Now you might inquire, well, why don't astronomers simply wait until methods improve? Why don't they obtain more precise measurements? And they are doing that. The Gaia telescope gauges the parallax of over 1 billion stars with unprecedented precision. The Hubble Space Telescope has been gauging Cepheid variables in neighboring galaxies for decades. The James Webb Space Telescope, the newest and most powerful space telescope we possess, is making observations that might assist us in calibrating the cosmic distance ladder more accurately. Yet, here's the matter. Even as we render these measurements more precise, we're discovering that errors we thought we'd eliminated still exist. We're discovering new systematic error sources we hadn't considered. For example, it turns out that type Ia supernovae brightness isn't quite as constant as we thought. They vary somewhat depending on the stellar system's age and the companion star's composition. This signifies the calibration we performed was slightly inaccurate. That signifies our distance measurements to even more distant galaxies are slightly inaccurate. This is the perpetual complication of science. Each time you enhance your measurement, you discover you were incorrect before, yet in ways considerably more subtle and fascinating than you thought. This is what NASA deals with. They're not deceiving you when they inform you how distant things are. They're simply not disclosing the complete, complicated, messy reality, because the complete reality is they don't understand as precisely as they'd prefer to. Allow me to inform you about a concrete example. A crisis existed in cosmology a few years ago. NASA researchers utilizing the cosmic distance ladder to gauge the Hubble constant obtained a value of approximately 73 kilometers per second per megaparsec. That signifies for each megaparsec of distance, about 3.26 million light-years, the universe expands at an additional speed of 73 kilometers/. Yet observations of the cosmic microwave background, the light remaining from the Big Bang, suggested the Hubble constant should be approximately 67 kilometers per second per megaparsec. That's about a 10% difference. And that difference is statistically significant. It's not a measurement error, it's a genuine discrepancy. Which measurement is accurate? Both researcher groups are competent, both have gauged carefully, both have scrutinized their work, yet they obtain different answers. This is designated the Hubble tension, and nobody understands how to resolve it. Some cosmologists think a systematic error might exist in the cosmic distance ladder. Others think something might be incorrect with our understanding of the cosmic microwave background. Some wonder if new physics exists we haven't discovered yet. Yet the point is, NASA researchers cannot simply inform you the Hubble constant with certainty because they're genuinely uncertain. They're not certain which measurement is more accurate. This is why NASA qualifies its statements. When they publish official values, they provide you a range. The Hubble constant is between this and that. They're being appropriately honest about the uncertainty. Now, here's something fascinating to consider. Why do you think we even concern ourselves with gauging distances in space? What difference does it make? Well, it matters for science. It matters for comprehending our position in the universe. If the Hubble constant is 73, then the universe possesses a specific age. If it's 67, the universe possesses a different age. That's not insignificant. The universe's age matters for comprehending how stars formed, how galaxies formed, how the universe has evolved. Get the distance measurements incorrect, and your entire picture of the universe's history is incorrect. Yet here's what I genuinely want you to comprehend. The fact that we cannot gauge cosmic distances with perfect precision doesn't signify our measurements are meaningless. The cosmic distance ladder, with all its imperfections, has taught us tremendous things about the universe. We understand the universe expands. We understand it's billions of light years across. We understand distant galaxies are billions of years old. We possess a detailed map of the universe's structure. We comprehend dark energy and dark matter. We've determined the universe consists mostly of material we don't comprehend. None of that would be feasible without the cosmic distance ladder, even with all its limitations. What NASA struggles with, what they cannot simply inform you, is that we're at the edge of what's currently measurable. We've gauged what we can gauge with our available tools and methods. We've pushed those methods approximately as far as they can go. To understand more, to gauge more precisely, we require either new telescopes or new methods or a deeper comprehension of astrophysics. We're not there yet. So NASA informs you what they understand, yet with appropriate qualifications and uncertainties. And that's actually an indication of sound science. If NASA simply confidently informed you the universe is exactly this immense and everything within it is exactly this distant, I'd be skeptical because we inhabit a complicated universe gauged with imperfect tools by researchers attempting their finest to comprehend something greater than themselves. The uncertainty isn't a failure. It's evidence that we're pushing at the boundaries of human understanding. So that's why NASA cannot inform you the straightforward reality about space distances. It's not because they don't understand. It's because the reality is complicated. It's because measurements possess errors. It's because the cosmic distance ladder is a beautiful yet flawed instrument. It's because the universe is more immense and stranger than we can fully comprehend. Yet the fact that we can gauge distances to the observable universe's edge at all, the fact that we can take light traveling through space for billions of years and employ it to determine how distant it originated, that's pretty remarkable. And the fact that we acknowledge our uncertainties, that we're honest about our method's limitations, that we continue working to enhance our measurements and detect our mistakes, that's the finest aspect of science. So, when NASA informs you a distance and they provide you a range and they discuss uncertainties and error margins, don't consider that an evasion. Consider it honesty. Consider it evidence that they're taking their measurements seriously, that they comprehend their instruments and methods' limitations, and that they're attempting to inform you the reality, the complete reality, even when the complete reality is messy and complicated and doesn't fit neatly into a brief statement. The reality about space distances is this. We're gauging an infinitely vast universe with finite tools. We're improving constantly, yet we have progress remaining, and that's acceptable. That's how science functions.